We spent the last 5 weeks of school studying kinematics, and we defined kinematics on the very first day of Physics 20 as the study of motion without regard to what's causing that motion. In other words, we were paying attention to the speed and the velocity and the time and the distance and the displacement and the position of a car or a ball or an animal or a person. But we didn't pay any attention whatsoever to what caused that motion to begin with. What made the car speed up? Hey, it sped up at a rate of 2.3 meters per second squared, but what made it speed up at a rate of 2.3 meters per second squared? Or the ball came to a stop and decelerated very, very quickly as the baseball player, caught it. But what made it slow down very, very quickly? That's what we're going to pay attention to in this unit a little bit more, is what makes something speed up or slow down, what causes the motion of something. Dynamics is the study of motion, as is kinematics, but it's the study of motion with regard to what causes the motion. In other words, it's the study of motion paying attention to forces. Because really, we all know this, right? It's forces that cause motion. Matt's desk is at rest right now. It isn't going to go anywhere unless we apply a force on that desk. Now, in the last unit, we could analyze the motion of that desk as soon as I apply the force on it, but we knew nothing about the force itself. This unit, we're going to learn about the force that causes that motion, or the force that causes it to slow down and stop, friction. The study of motion, paying attention to or with regard to what causes the motion, or in other words, paying attention to forces. Now, let's define a force. It's a new term for us in Physics 20. It's not a new term for you guys overall because you've learned this before in grade 6. Grade 6, you studied flight, and you learned about different forces when you learned about flight. The lift force, remember that? The lift force, a drag force. Okay, you learn about all these different forces. Do you guys remember what the definition of a force in general was? Not specifically the lift force, but just a force. It's the easier than that. Easier than that. Don't try to make it harder than it has to be. You don't have to sound fancy at all here. It's the easiest definition in the world, Luca. It's a push or a pull. It's just a push or a pull. That's it. A force is a push or a pull. Now, that doesn't necessarily mean that we are pushing it or we're pulling it. It could be wind that pushes it, or it could be a tow truck that pulls it. But a force in general is a push or a pull. And there's a million different kinds of forces, a million different things that can push or pull, and a million different things that can be pushed or pulled in a million different ways. But in general, it's a push or a pull. Now, what you didn't learn in grade 6 is the effect of a force. A force can do two things, one of two things, or even both of those two things. Anybody want to take a stab at what one of the things a force can do is? Yeah. Well, it can push it. We're not going to go back to the definition of a push or a pull, because that's actually not the effect, right? That is the force. The push is the force. The push is, the pull is the force. The effect of a force isn't the push. The force is the push. What's the effect of the force? What's the effect of a push? Yep. Okay, it can stop something. Good. So a push or a pull can stop something. It can move something that's not moving, so it can speed something up. It can stop something. It can speed something up. Maybe it slows something down without actually stopping, right? Maybe you change the direction of something. Okay? You got a car moving straight on a highway, you turn the steering wheel, there's a force of friction between the wheels and the road to cause the car to turn, to change direction. All kinds of different things. All of those things that we've mentioned, though, in general, boil down to this. A force can accelerate an object. That includes speed up, slow down, stop, change direction. All of those things are under the umbrella of accelerating an object. Even changing direction. A car's traveling down the highway at 100 kilometers per hour. It goes around a turn. It stays going at 100 kilometers per hour. It doesn't speed up. It doesn't slow down. It just changes direction. That's still an acceleration, because acceleration is not the change in speed over change in time. It's the change in velocity over change in time. And if you're changing direction, you're changing velocity. So even if the speed stays the same, if the direction changes, that's still an acceleration. So what can a force do? It can accelerate an object. Speed up, slow down, start an object moving, stop an object that's already moving. It can change the direction of an object. Boy, that seems to take into account everything, right? So what else can it do then? Nothing? Well, there's another thing. Clearly, there's 2 blanks there. What else can a force do besides cause an object to accelerate in one of those ways? When I put my head on the pillow at night, my head has a certain mass. This is a force of gravity pulling down on my head. That will cause my head, okay, to accelerate downwards towards my pillow. When I gently place my head on that pillow, I apply a force on that pillow. I'm not causing that pillow to accelerate. The pillow's not going anywhere. What am I doing here? What am I doing here? Yeah, I'm deforming it. So a force can accelerate an object. Hey, I can accelerate a pillow. I can pick it up and throw it, but I can also deform the pillow by applying a force. When you bounce a basketball on the ground, bounce a basketball on the court, you're decelerating that object, right? And then very quickly, it's accelerating in the opposite direction. You're causing an acceleration. But at the same time, you're deforming the object. So sometimes you just accelerate an object. Okay, when I apply a force on a desk, I accelerate the object. Sometimes I'm just deforming the object when I put my head on the pillow at night. Sometimes I'm doing both. When I bounce a basketball, I'm accelerating the object and I'm deforming the object all at the same time. Does that make sense? You ever wonder you ever stop and think about this? You put your hand on the wall, lean against the wall. You're not causing the wall to accelerate, are you? Did you hear the wall when I did that? Did you hear that? Did you hear it? What have I done to the wall? I deformed it a little bit, not very much, right? If you had some kind of measuring device that could detect ever so tiny, minuscule changes in shape, you would have found when I leaned against the wall that the wall went from straight to something like this. That's exaggerated, right? This is what it was. When I put my hand on it, it went to this. Just not quite as pronounced as that, that's all. Even when I knock on the desk, did I cause the desk to accelerate? No, I didn't. The desk didn't accelerate at all. What did I do? Well, as much as you don't see it, I actually deformed the desk a little bit when I did that. I also deformed my fingers, right? Because if I applied a force on the desk applied a force on me, so my fingers and the desk would both be deformed. Make sense? When you bounce that basketball, you see the basketball being deformed, but the floor is also deformed, right? Okay, one more term before we flip the page here. The net force. The net force. Where have you heard that term net before? Not in the context of like, oh, he fell off the high wire as he was doing the tightrope walk and fell into a net. Okay, not that kind of net. Where have you heard the term net in some other context, Julian? Okay, a net income. Good example. Good example. A net income. My gross income is something like $200 a month. Something like that. More or less. It might be a little bit different than that, but not much than that. So my gross income is $200 a month. But then maybe I get a special Christmas bonus because I'm so good. Because I'm so good. So we add to that 13 cents. So now I'm at $200.13. But then they take off another $50 in taxes. And then they take off another $30 for pension. And then they take off 13 cents because they realize they gave the bonus to the wrong person for being so good. And then they take off a little bit for health insurance and all that kind of stuff. And in the end, I'm left with this. What is that now, by the way? $100? I'm left with $100. That's my net income right there. So this would be my gross income. This would be my net income. I don't know about you guys, but how many of you guys have a job? You guys probably don't get very much tax taken off. Okay, I get a lot of tax taken off. I don't make a fortune, but when you get a real job, when you grow up and get a real career job, you get a lot of money taken off in taxes. Okay, after that money's taken off, they call it your net income. They should call that your gross income, because that's the gross number right there, not that number. That's the number that makes you excited. You see that pay stub and it's like, oh boy, I'm rich. And then you realize, oh, I only got half of it. I only get to take home half of what they give me in the first place after they take off everything. That's literally what it is. It's not much more than half. I get not much more than half of what my gross pay is. My net income is what I started with plus everything else, plus my bonus, plus the negative of my income tax, plus the negative of my pension. It's all of the monies for that month added together, paying attention to positives and negatives. My net is the total amount. Right? Total we think of as being a bigger number, but total can be a smaller number. 200 plus 13 cents, 200 plus negative $50. It's the total, or the unbalanced, when all is said and done. The net force would similarly be the total force acting on something. Now, if your net force is 0, then we say the forces are balanced. Doesn't mean there's no force. There could be 3, 4, 5, 6, 7. There could be 1,000 forces, but they balance each other out. There are forces, but there's no net force. If the net force is not 0, then we have what we call unbalanced forces. And it's unbalanced forces that cause motion. You can have all the forces you want, but if the net force, the total force, the unbalanced force is 0, then they don't really do anything. Things keep doing what they're doing. If the net force is something other than zero, then motion happens. You either speed something up or slow something down or change the direction of something. Yep. Depend upon the ground, right? The question, if you didn't hear that, was how much force would it take to crack the ground? I've cracked the ground before. When you drop something on a piece of ice, or when you drop a thin layer of ice, right? There's a puddle outside. It's the fall. It's one of those days where it's just starting to get below zero, and there's a thin layer of ice, and you step on that puddle, or you drop something, you crack it, right? But again, it depends upon the degree of an earthquake, right? There's magnitude 3 earthquakes, and there's magnitude 8 earthquakes, which magnitude 4 earthquake isn't half as strong as a magnitude 8 earthquake. Magnitude 8 is exponentially larger than magnitude 4 earthquake. So how much force would it take? I mean, that's a pretty tough question to answer, right? Because it depends upon what you're talking about with cracking the earth, right? Another term, inertia. You ever watch Bill Nye? Well, you know that inertia is a property of matter, right? Well, inertia is a property of matter, but what is it defined as? Inertia is the tendency of an object to resist a change in motion. In other words, if something's at rest, it wants to stay there. If something's moving, it wants to stay moving at a constant speed in a straight line. It doesn't want to change motion. And it depends upon one thing. Anybody know? Nope. Depends upon mass. That's it. The heavier something is, the more inertia it has. Doesn't matter whether it's moving or not. A lot of people think it has to do with its speed. It doesn't. Something's moving fast, it might be hard to stop something that's moving fast, but it's not hard to slow it down or speed it up. Inertia is not the tendency to make it not stop. Inertia is the tendency to resist a change in what it's doing. The only thing that affects that is mass. The heavier something is, the harder it is to speed it up or slow it down, to change its direction. The harder it is to change its motion. Yep. Sleeping teenagers that have a lot of inertia, yes. It's difficult to change what they're doing. Yes, it is. Teenagers in general, because if they're doing something bad while they're awake, it's also difficult to change what they're doing. So in that sense, teenagers generally have a lot of inertia. Static equilibrium. Static equilibrium is when we have an object at rest with F net equal to 0. What's the result of that? If the net force is 0, if there's no unbalanced force and it's at rest, hey, we know by inertia that it wants to keep doing what it's doing. So what does it do? It's going to stay at rest. Because it's got inertia. Inertia keeps it doing what it's doing. It's at rest. Stays at rest. That's static equilibrium. Translational equilibrium is when we have an object in motion at a constant velocity. Once again, we say the net force is 0. Because if the net force wasn't 0, it would speed up, or it would slow down, or it would change direction. What's going to happen to it? It's going to keep going. Nope. Well, no, not necessarily. It's going to keep going in a straight line, same speed. The question from Nathan was, do we have to have a perfect system, no friction, whatever? No, because the net force is zero doesn't mean there's no forces. It just means the forces are balanced. So you get friction acting to the right, slowing something down. As long as you have something acting to the left to speed it up, those two forces can balance, right? So you don't have to have a perfect system here. You just have to have a net force of zero. Finally, Newton's first law, otherwise known as the law of inertia. There's two aspects to Newton's first law. First one says an object at rest. What's it going to do? Stays at rest. Second part is an object in motion. Stays in motion. Now be careful with this one. It stays in motion in a straight line. So even if it's moving in a turn, it's going to keep going in a straight line, constant speed. So it's not going to speed up, slow down. Both of these are going to keep happening forever and ever and ever and ever and ever. Until what? Until you apply a force? No. Until you apply an unbalanced force. Until you apply a net force. Until a force other than zero is acting on it. Let's say until an unbalanced force. Hold on, guys. Don't back up, please. Object at rest stays at rest until an unbalanced force acts on it. An object in motion stays in motion, straight line, constant speed, until an unbalanced force acts on it. Might have forces, okay, but as long as they're balanced, this is going to keep happening. It's not until they're unbalanced when something changes. All right.